Here's kind of an interesting example that has a little bit of a twist to it. We're asked to integrate from 0 to root 2 over 2 of arc cosine of x divided by the square root of 1 minus x squared dx. Okay, and there's a couple things that's interesting about this. First thing that kind of catches my eye is that this integral has an inverse trig in the integrand. Normally when we do inverse trig functions, we're getting an inverse trig in our answer. I don't think up to this point we've seen an inverse trig function in one of these integrands. And so this is one of those types of examples that, at least for me, I don't know if I would know immediately how to do this without having seen it before. You know, possibly if we thought about it for a good long while, we might come up with this idea. But I hesitate calling it a trick. But there's just this algebra procedure that's very clever that'll help us integrate this. Okay, so here's the idea, and the logic as to why we would do this as well. Because we're less familiar with inverse trig functions, let's see if we can somehow rewrite this integrand in terms of maybe another variable or something that doesn't have inverse trig expressions in it. So the idea is this: we're going to take that arc cosine of x, and we're going to temporarily call it y, okay, or u, or just pick a letter, but y is a pretty standard letter. So we're going to temporarily call this guy y for the short term, and that way I can take out the numerator and replace it with a y. Now the reason this works is because if you look at what's left, if you look at these remaining terms, basically in effect 1 over the square root of 1 minus x squared, that's or at least almost is the derivative of arc cosine. So if we found y prime, this would be the derivative of arc cosine, which, if you recall from a few videos ago, would be negative 1 divided by the square root of 1 minus x squared. So it's almost in effect like a u substitution. You have a u, and then what's left is du, or in this case y, and then dy, or y prime, or what have you. Okay, so let's do this substitution here. All right, the numerator will be just y, and then the 1 over square root of 1 minus x squared needs a negative. So I'll give myself a negative, and I'll put a negative also on the outside. And the negative 1 divided by a square root of 1 minus x squared becomes my, or with the dx, becomes my dy. Right? This becomes my dy. So I've basically, in effect, done a variable substitution here. Now, one thing that needs to be stressed, this is a common mistake students make. They're tempted to say that the limits of integration are still 0 to root 2 over 2, but in fact that's not the case. And the reason for that is this: 0 to root 2 over 2 was the range or the interval for x. X ranged from 0 to root 2 over 2. There's no reason that y should also range from 0 to root 2 over 2. So we have to be a little extra cautious about that. So we have one of two options. We can either do a conversion and figure out what my new limits of integration are. That's totally acceptable. Or we can do the integration, and then after we do this integration, we'll write it back in terms of x, in which case we can use our old limits. Either way works fine. I don't really have a personal preference or anything like that. I'll tell you what. Why don't we just go ahead and find it right now? It'll save us a step. If you're comfortable converting the limits, I would suggest doing that because it's quicker. So let's do this. I'll actually do it on the next page just so we can save a little bit of time. So x is as low as 0 or as high as root 2 over 2. Okay, x is as low as 0 or as high as root 2 over 2. So x is 0 or x is root 2 over 2. But if you remember the conversion, what y was equal to arc cosine of x. So to find the equivalent y value, we're going to take these x's and plug them in for x and see what the equivalent y is. You can think of this as a conversion from x's into y's. So here y would equal the arc cosine of 0, and here y, let me erase that here. Y would equal arc cosine of root 2 over 2. Okay. Now you remember the arc cosine function is a one-to-one function. It's monotonic. So you plug these values in, and there should only be one answer. Now I'm not going to go through a lot of detail as to what the restricted domain and all that kind of stuff again is for arc cosine. But I'll just go ahead and tell you what these answers are. This would be equivalent to asking cosine of what angle would give you 0. Cosine of what angle would give you 0. And the answer to that would be cosine of pi over 2 would be 0. And then this is like asking cosine of what angle would give you root 2 over 2. Root 2 over 2. And the answer would be pi over 4. Cosine of pi over 4 would be root 2 over 2. So we have these two values, and these are the equivalent limits that we have instead of x. These are the limits for y. So we're going from pi over 2 to pi over 4. From pi over 2 to pi over 4. Okay, let's do the integration. This is actually quite simple now. We get negative y squared over 2, just a simple power rule. We don't have to convert back to x's or arc cosines or what have you. We can put a bracket with a pi over 2 and a pi over 4. Plug those in and subtract. So we would have, I'm going to do a little mental math in my head just to simplify this a little bit. Plug in pi over 4, you would get, let's see, negative pi squared over 32, and I did skip a few steps there, so just be careful with your algebra. And then you'd have minus a negative, which makes a positive, a plus. You get pi squared over, let's see, it'd be 8. Pi squared over 8. All right, so our final answer would be, let's add these together, get a common denominator and all that good stuff, and I think it would be 3 pi squared over 32. Now you might want to check my algebra on that, but assuming my mental math is decent, I think that this would be your final answer. Now what is this? What is 3 pi squared over 32? That would be the area under this curve, right? As definite integrals always are. This is the amount of area under this curve here from 0 to root 2 over 2. So this is a unique problem, but you're likely to see it again. If you open up your calculus textbook, you'll likely see a definite integral problem like this that has an arc sine or an arc cosine in it. So it's one of those things, once you've seen it once, then it's not so bad and you can repeat it. But again, these are basically just done by doing some sort of variable substitution, and that's how we work these guys out.